Machine learning is used in a lot of different applications. Automatic facial recognition, financial estimation, robots control, medical diagnosis, spam detection, automatic chat, automatic voice and speech recognition, weather forecast, risk management, analysis of people behavior, and so on. It is impossible to enumerate all applications of machine learning. However, it does not matter what these applications are. All these applications are usually only different expressions of a few number of typical tasks. In this way, the same algorithm used for fruits recognition, for example, could be applied to identify landmarks in a map for a robot localization. Both applications are dealing with a classification problem. In that set of typical tasks of machine learning that are the basis for a large number of applications, we can highlight classification, clustering, regression, dimensionality reduction, decision-making, and a few others. In clustering task, given some typically unlabeled data points, the goal is to group these points in such a way that points in the same group or cluster can be in some sense more similar to each other than points in other groups. Considering these data points, for example, we could choose to group these points in 3 different clusters. Measures for clustering usually are distance between cluster members, density of clusters, statistical distribution, and so on. Different algorithms will make use of different strategies and measures to perform the clustering task. In classification task, given a set of input data points and the classes they belong, or the labels, the goal is to identify to which class a new observation belongs. Most of the classification methods look to establish decision boundaries to separate the different classes. The many available algorithms will make use of many different strategies to classify data. In the regression task, given some data points, the goal is to learn a mathematical model capable to fit data with a curve, so that the curve passes as close as possible to all of the data points. This approach allows to predict the output for points that were not part of the original data. In dimensionality reduction, given a set of data points in a high number of dimensions, features or attributes, the goal is to reduce the number of dimensions under consideration. In this example, if I adopt this axis instead of the original axis, I would have all necessary information to perform a classification task, for example. In other situation, I could have a high number of inputs arriving from different sensors and I could choose only one of them or a few to pay attention. It is usual that we can have dozens or even hundreds of dimensions in some practical situations. Some of the benefits of the dimensionality reduction are lower data volume, less computing required, shorter analysis time, and so on. In decision-making, given a set of input data or information, or even an environment, the goal is to learn models, concepts, or policies that can make agents able to make decisions. If I have a robot playing soccer, for example, in a given situation my robot can be in front of a ball. Some possible actions for my robot are kick the ball, move to the left side, move forward, and so on. With the use of a learning algorithm and after some training, my robot can learn how to decide what is the best action to achieve his goal. Generalization is one of the most important concepts in machine learning. Let us consider that these blue points are my training data. My machine learning system can learn a set of different functions that can correctly fit my training set. For example, my system can learn to approximate these examples with a linear curve. My system can also learn to fit this training data with straight lines. Other possibility is my system to learn a sinusoidal curve. A polynomial curve is also possible to fit this data. Which function is the best one to describe my training data? In fact, in learning process, we are concerned with two questions. First, learning functions or models or concepts that will give us the correct outputs for the data present in the training set. Okay, all these curves are able to give us the correct outputs for the data present in the training set. Number two, learning functions, concepts, or models that can generalize to instances similar but not identical to those in the training set. So we can understand generalization as the capacity to correctly predict values for unseen data. Here we have examples of very different outputs for the same point. The prediction for this value will strongly depend on the learned curve. In next topics, we will discuss strategies to deal with generalization. Underfitting is also a very important concept in machine learning. It occurs when a model is not capable of adequately representing the training data. In other words, it has a high training error, nor generalize to new data. It typically occurs due to one of two situations. First, the system was not trained enough. In this example, we have a curve during a learning process. The training error will typically decrease with more training. The second situation is when the model is not complex enough to adequately represent the data even with more training. In this example, we have a first-order model that may not be suitable for representing the data. The training error typically will not decrease with more training because the model is not complex enough to represent the concept. In well-trained systems, typically curves will tend to fit the overall trend of the data. In other words, we can have the training error bigger than zero. In some practical cases, we don't want the training error equal to zero because the training data can have some noise, for example. If the system is trained for too long, it tends to learn the noise and inaccuracies of the data. Models that are more complex than necessary will be learned, generating lower training errors. Eventually, we can have a training error equal to zero, but reducing the performance of the system with new data. In other words, we can have high generalization errors. This situation is called overfitting. In other words, the system is super specialized and it's not capable of suitable generalization to points close to those in the training set. We usually don't give all examples that we have, that is, all available data, at the same time to train the system. It is common that we can divide this data in at least two subsets. The first is the training set, that will store the data that we use to train the system. Training the system means adjust the free parameters of the model. And the other is the test set, that will store the data that we will use to evaluate the system, or the learned model. These are two different data, and the data that we will use to test the system should never be used until the end of training. Cross-validation is a strategy to estimate how good is the model generalization in the training phase. It is also eventually used to stop the training or to change some parameter in the training. The idea is to divide the training set between the training set and a validation set. What is a validation set? It is a set with data that was not used in the training phase that will be eventually used to evaluate the training or to monitor the training. A suitable proportion between sets must be defined. Some practical values for this proportion are 50, 25, 25 or 60, 20, 20 if we have a lot of data, and about 90, 5, 5 if we have a few data. When we start working with learning systems, we usually think that we must train the system indefinitely. This is not true. Of course, we usually spend a lot of time training the system, but we cannot train the system too much. In this graph, we have the system error and the training time. As we can see in the blue curve, the more we train the system, the smaller the training error, that is, the error for the examples in the training set. However, this is not the same behavior that we have for the data present in the validation set. The validation error usually decreases, reaches a minimum value, and so increases. This happens because when the system starts learning, the learned model is too simple to fit the data. With training, more complex models are learned, and in some points the model is suitable for both training and validation. If the model is too complex, the system loses its capacity to generalize for the data close to those in the training set. For this point forward, the validation error will always increase. In other words, this is the moment when we must stop training. If we stop the training in this point, we can avoid both underfitting and overfitting. There are several ways to create a validation set. We'll discuss some of them here. One of these methods is the holdout method. In this method, part of the available data is reserved to be used for validation, that is, this data is holdout. Typically, errors in the training set and in the validation set are evaluated at each time step during all the training phase. As always, the test set must not be used until the end of the training process. There are some important remarks in the holdout method. First, since we have reserved some data to the validation set, the training set is smaller. Second, we must pay attention to the data distribution in both sets. If the training and validation sets have data with different distributions, the results can be distorted. In the repeated holdout method, the holdout strategy is repeated several times but with different data. At each iteration, examples from the available data are randomly selected and they are divided according to the established proportion into the training and validation sets. The system is fully trained using this data and validation sets. The data selected to belong to the validation set will not be used for training in that particular iteration. After the training is done, a second iteration will take place with different randomly selected data. In this iteration, different examples will be sorted to the training and validation sets. After a number of iterations, the model with the smallest error for the test set, for example, can be selected. A remark with the repeated holdout method is that if some examples are selected more or less than others for the training or validation sets, results can be distorted. A very used approach in practice is the k-fold method. The available data is divided into k partitions. In the first iteration, the first partition is used as a validation set and all the remaining data is used as training set. The system is fully trained with this data. In the second iteration, the second partition is used as validation set and all remaining data is used as training set. Again, the system is fully trained with this data. This process is repeated k times, each time using a different partition for validation. Each partition is used for validation exactly once. After k iterations, the model with the smallest test error, for example, can be selected. This strategy has a more structured way to divide the available data between the training and validation sets. The leave one out method is a particular case of the k-fold where the validation set has exactly one sample. In the first iteration, the first example of the available data will be removed from the training set. This single example will be the validation set for that particular iteration. The system is fully trained with this data. In the second iteration, the second example will be selected for the validation set, and so on. The number of iterations will be the number of examples. The process follows exactly like in the k-fold method. There is an important remark regarding the data distribution in the training sets. Ideally, Sampling in all datasets, training, validation, and test must have the same data distribution than the total available data. Particularly, 1. Sets must preserve the same relation of the number of samples from each class present in the original data. Suppose that we have this data as the available data with only 8 examples of the red class and 21 examples of the blue class. Now, suppose that after splitting the available data, we'll have only 5 of these data points as training examples of the red class. There is no reason why I should select only 5 of the examples of the blue class for the training set. If I do that, I will be losing important information for the classification. 2. Sets must contain samples spread over all regions of the domain. Suppose that I have these data points as my available data. If I choose my training set points only in one region of the domain, the learned model will never be able to learn in these blind regions. In other words, it is extremely important that all the sets, training, validation, and test can always keep the same distribution of the available data. Let's consider that our problem has 2 dimensions and that the data points are distributed as shown. In order to normalize the input set, we need to perform 2 actions. The first one corresponds to shifting the data points to the center of the axis. Or, in other words, to transform the data points distribution in a distribution with mean equal to 0. I can do that applying the relation mu in a particular dimension is equal to 1 over n sum over I from 1 to n, where n is the number of data points of xid. So xid will receive xid minus mu. This is the expected result of the shift in data points. The data points distribution is expected to have mean equal to 0. We can see now that the distribution of our data points is much bigger in one of the dimensions compared to the other. Because of that, the second step corresponds to the variance normalization. Sigma squared equals to 1 over n sum from I equal to 1 to n of x minus mu d that we forced to 0 squared. So xid will receive xid divided by sigma squared. We can see the expected distribution after this transformation with the data well distributed in all axes. Of course, we must apply this normalization to all sets, training, validation, and test. And why should we normalize the input data? Input data distribution has implications in the shape of the cost function used in some learning process. We will better discuss the cost functions further. Although most of the learning algorithms are able to learn over unnormalized data, we have 2 points to remark. First, if data distribution has 0 mean, it will probably require less learning steps to tune variables in models. So, in this example, starting from some random point that is not too far from the origin, the number of steps tend to be smaller if the cost function is close to the origin. Second, in a symmetrical cost function, the step size, or the learning rate, tends to be more effective to find the center of the function. As we can see in this example, it is more effective to walk over a regular surface than to walk over an irregular one. In this way, normalization is a technique that can speed up the training process.